Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 1 for this week, and we're going to be talking about something called the Lee Trough, and it's called that because it occurs downwind of a mountain range, okay? And we see this east of the Rockies a lot and to a lesser degree east of the Appalachians, but it's still there and can still play an important role. So when I heard the word Lee or thought of it this afternoon, this came to mind. Do you remember Paul Simon's old song, 50 Ways to Leave Your Lover? So just drop off the key, Lee, and get yourself free, okay? I don't know why I had that association in my mind, but it's there. All right, so let's go on ahead and review a little bit. And there is going to be some math in this. So if you absolutely detest math, then it may be time to skip this video and wait for the next one on Friday. But I feel like it's necessary in order to explain a couple of these concepts. So we've talked about vorticity before, what's constant and what isn't. Well, first of all, there are two types of vorticity. Planetary vorticity is caused by the Earth's rotation, and it is proportional to the sign of the latitude, okay? So obviously the latitude gets larger and larger as you go farther and farther north, so planetary vorticity is 0 at the equator and is maximum at the North Pole, okay? Then there's relative vorticity, which is caused by weather systems, and that can be caused a couple of different ways. You can have curvature in the flow, okay, or you can have wind shear, which actually creates either anticyclonic rotation or cyclonic rotation, okay, counterclockwise or clockwise. So relative vorticity is weather systems, okay, and absolute vorticity is the sum of the two. So you add up the vorticity caused by the Earth's rotation and the vorticity caused by weather systems, and you have absolute vorticity. Now, in physics, we talk about things that are conserved and not conserved. And in other words, if it's conserved, it doesn't change. If it isn't conserved, it does change, okay? So absolute vorticity is not conserved. It does change, okay, for a variety of different reasons. But something called potential vorticity is conserved, and that remains constant. Okay, so you with me so far? So let's, one more thing, want to review this whole thing about cyclonic vorticity versus anticyclonic. If you had a protractor, you remember those things where you spin around a point? If you spin that protractor in a clockwise flow, in a clockwise manner, and it follows the flow, then that is anticyclonic curvature, okay, or the curvature like you would get around a high pressure area. If you rotate the protractor in a counterclockwise manner and it follows the flow, then that is what we call cyclonic vorticity or cyclonic curvature, okay? Something akin to a low. All right, so let's move on along here. This is where we get into a little bit of the math. And for whatever reason in physics, a lot of times Greek letters are used. So this is relative vorticity, this is the Earth's vorticity. You sum those together and you get absolute vorticity, okay? And I'm just being redundant here by lines 2 and 3. Now, we already said that you sum these two and you get absolute vorticity. If you divide that by h, which is the height of an air column, then that is called potential vorticity, and that remains constant no matter what is going on. So here's my very poor man's description, or not description, artist rendering of a mountain range, okay? Isn't that pathetic? All right. So you have an air column that goes all the way from the ground up to the top of the tropopause, or top of the troposphere, which is called the tropopause. As that air column moves over the mountains, it shrinks vertically, okay, it has to, but as a result, it grows horizontally. Well, if you have horizontal divergence, then that's usually associated with high pressure areas because the air diverges and it sinks, okay? And so that's associated with anticyclonic vorticity or anticyclonic curvature. And then when it gets east of the mountains and gets back to its normal height, then it grows vertically, but now it converges horizontally. And convergence in a horizontal manner is associated with cyclonic vorticity or cyclonic curvature, something related to a low, okay? So Now I get to use my telestration tool and hope that this actually works. So I'm going to leave this equation down here in the right-hand corner, okay, so we can refer to it. And my little z's there indicate where the mountain range is, okay? Now, let me pick this arrow here. So let's say we have a wind out of the west-southwest, okay? So it's going like this. Okay, and then it gets to the mountains and the column starts to shrink vertically, okay? So H is going down, right? That means that the numerator has to go down as well in order for this value to remain constant. Well, we got a problem here. F, the Earth's vorticity, is getting greater because it's going north. Remember, it's proportional to the sine of the latitude. So the more north you go, the higher the planetary vorticity is. So if H is going down and this is going up, then this, the weather system vorticity, has got to go down quicker than this is going up, okay? So that both the numerator and the denominator are getting smaller. Well, if this is getting smaller, if that's getting smaller, that means that you are decreasing your vorticity. And that means that that's associated with high pressure, anticyclonic curvature. So it's going to start to curve in an anticyclonic manner. Okay? Now, it's heading south because it curved anticyclonically. All right, so H got bigger again, which means that this has to get bigger. But we have a problem again. The air is going south, so it's losing the Earth's vorticity. And so if this is going up and this is going down, this now has to go up faster than this is going down. And so it starts to curve cyclonically. Okay, it changes and starts to do one of these. Now, as it continues to curve like that, it starts to head back north. Well, H isn't changing because we're done with the mountains, okay? We don't have to worry about those anymore. So if H is constant, then this has to be constant, but we know that F, the Earth's vorticity, is going up because it's going north. So that means this has to go down by the same amount that this is going up. So if the vorticity is decreasing, the relative vorticity, it starts to curve back anticyclonically again. And what you many times will get is a series of waves that will get less intense as you move along to each wave. But this is basically the main Lee trough right in here. And air converges along troughs, so you can get thunderstorm development along those. And east of the Rockies, the Lee trough is so strong that you can actually get what we call cyclogenesis, or the beginning of a low pressure area. And sometimes those can become very, very intense storms if there's some other things going for it. So, and the placement of this trough is critical because when air comes down off the mountains, it sinks and warms up and dries out. But east of the trough axis, the winds are more southerly, and so that's drawing moisture up from the south, okay? And that can sometimes lead to thunderstorms along and east of the trough axis, which would be in here. And I think some of that actually happened today because most of the thunderstorm activity was in eastern North Carolina. There was very, very little as you headed back toward the mountains. Okay. I hope that made just a little bit of sense. I love math. I always have. In fact, I always told people that in college that I would much rather have 10 hard math problems due the next day than have to spend 3 months trying to write up a term paper and read 6,000 pages. You know, that to me was what was really hard, okay? If something was due tomorrow and I had to think a little bit about numbers, I could handle that. But that long extended stuff, that was not for me. Okay, that is bonus weather video number 1 for this week. The next one will be coming up on Friday, and of course the next daily weather update will be coming up tomorrow afternoon. You all take care, everybody, and we'll talk to you soon. See you later.